Thank you very much, Mr. Chairman, ladies and gentlemen. I know there's no translation available, but I believe you will be able to follow my presentation with the help of the slides. After all, I should apologize. It's been 18 years since I first visited this conference, and my Serbian should have improved by now, but I hadn't managed. Anyway, I would like to spend the next 17 to 20 minutes discussing with you the issue of zero energy buildings, or nearly zero energy buildings, their potential perspectives and the probabilities for the future. And this is more or less the outline of my presentation. So I think you will agree with me that it has been quite a long way and quite an evolutionary way from the so-called happy energy eaters of the 1970s, buildings without any thermal protection, with a very low efficiency of the air conditioning and heating systems, over the insulated buildings of the 80s, through the passive buildings, which were perhaps more of a trigger for the development than a real trend, to the low energy buildings of the 2000s and to the zero energy buildings, which are the buildings that will follow us for the decade to come. And this evolution is probably mirrored best in the regulatory framework development on a European level. I'm sure you're aware of it. It started with the famous Energy Performance of Building Directive in 2002. 2010 came the recast, which foresaw the nearly zero energy buildings and a uniform methodology, cost optimal goals for each country member, smart metering and things like that. And last May we had its follow-up, the 844, the recast of the Energy Performance Buildings Directive, which sets the trend for nearly zero energy buildings of the whole stock, not only of new buildings, by 2050, which foresees the integration of information and communication technologies in the building sector, which also foresees the necessity to support electric vehicles, because it's very nice to speak of emission-free vehicular traffic, but if you don't have in the urban environment enough charging stations, and this is easier said than done, then I'm not really sure that you're going to have electric vehicles. And which also calls for a long-term strategy for the renovation of buildings and for facing energy poverty, which is becoming more and more of an issue in Europe. Now, obviously, the regulatory framework is a very complicated matter, and I wouldn't want to spend too much time on it, because it calls for anything from the standards on calculating losses and loads to how the connection to infrastructure has to be established, and how the various ways of energy used, like in the presentations before, can be specifically expressed, measured, certified, and utilized. But what is more important is to agree, and this has a lot to do with the architect's approach, I have to admit, that if we want to have zero energy buildings, of course we have to start with the architect's work. It hurts me as a mechanical engineer to say, but the 50% plus one of the success of a zero energy building is the architectural work. If our colleagues do their homework properly, then it's easier to make zero energy buildings. If the surface to volume ratio, the orientation, and the window to wall ratio and everything else is not efficient, then it's very difficult to achieve the goal. So we have to have thermal protection, solar design, passive and low energy cooling techniques, heating obviously also, high efficiency heating, ventilation, air conditioning systems, and decent ways to integrate the renewables. And of course also we have to have the buildings integrated into the whole infrastructure, because more and more we speak of bivalent energy flows, and that makes life more complicated. So I think there are three questions that have to be answered. If we need mandatory thresholds, and to what extent? What does the N, nearly zero, stand for? And where and when are renewables to be considered? And if you have a look through the table that synopsizes restrictive criteria and the regulations of a series of European countries, then you will see that there is a mandatory, directly or indirectly, U value practically in every country. Thermal bridges are in almost every country considered as a separate problem. But when you start to move to the airtightness, let alone to the design of the facades, the regulatory framework gets a bit more relaxed. The results of the framework so far have not been bad, to be careful. So if you see what more or less the expected energy requirements for contemporary buildings are, based on the level of regulations of the still valid directives of the 2012 direction, then you would see that depending on where you are, from Nicosia and Cyprus via Athens to Prague and to Bucharest or Paris, you come up with something between 70 and 150 kilowatt hours per square meter of energy, primary energy that is. And in order to move in that sense, of course it starts with the thermal protection, and insulation is and remains the most cost-effective way to reduce the building's energy requirements. And if you have a look at the minimum requirements for the U values for windows and walls, and I'm listing here cities because in many countries you know that we have regional requirements, it's not a uniform thing. You have anything from 1.1 for windows or for 0.05 in walls in Copenhagen to 2.8 in Malta, with anything else from Malta to Belgrade to Copenhagen in between. Obviously, one cannot compare those values to each other because we have different climate conditions, as you can see in the heating degree days map on the right. So if we try to normalize this, and here I have divided the U value with the number of heating degree days plus a correction factor so that it makes sense, then you can see that there is a reason behind it. When it comes to the windows, you can see that more or less we have Southern Europe, Central Europe and Northern Europe with similar performances, but it's more interesting, especially in the walls and the opaque building elements, the U value requirements are fairly within the same line of approach. How do we achieve this? Well, obviously by using insulating materials, and I don't want to go into this field. I love it very much and I've been working with it for God knows a quarter of a century now. But it is clear that if we want to move to the U value limits of 0.05, especially in Northern Europe, we cannot go on using conventional insulating materials because very soon we will need 50 centimeters of insulation material on a wall that is perhaps 15 or 20 centimeters thick, and this is not necessarily reasonable. So I think that especially in the northern countries, the move towards aerogels or vacuum insulated panels will become a trend in the coming decade, not necessarily so in more moderate climates like in southern and even central Europe. But what is also important is we need other things apart from thermal insulation. We need, for example, cool materials, i.e. materials that are capable of re-emitting the thermal part of solar radiation and reflecting a part of the optical radiation also, so as to reduce cooling loads. And you can see in this picture material that we have developed a couple of years ago in the university, and it is available in the market now. We have a composite thermal insulation material with a ceramic tile that is really cool. It has a reflection and an emission factor of 70% almost in the thermal spectrum. And it reduces external temperature, surface temperatures by about 8 to 10 degrees and the internal temperature of the roof by perhaps 5 or 4 degrees. And if you think that this is not a lot, then it's enough to have to be reasonably well within the thermal comfort areas, whilst with a conventional insulation material this would not be the case. So there's a lot of work to be done in this field, and I'm sure that many colleagues are working on this. Now, the more our buildings become transparent and light structured, the more we need thermal storage, which tends to be a forgotten quality sometimes. And phase change materials, for example, embedded in the plaster or in the fiber boards are an excellent idea, and there are some very nice materials on the market available. The question is which material, at which temperature of melting, how much of it, and where to apply. Because if we want to try to calculate and optimize this, and this is clearly a multi-parameter optimization that we have to carry out, it depends if you have a single plan area office or a very conventional layout. It depends on the internal loads, it depends on the use. So you can see that in the example of the same area with different layouts, you can have reductions in cooling loads of perhaps 5, 7, 8%. Don't expect miracles, but 5% on this plus 3% from the cool materials plus another 2% from the glazing, you end up with 15 to 20% savings without even having entered the boiler room or the air conditioning room. So this is something that has to be approached in a tailor-made optimization way. So we come to the role of HVAC and renewable systems, which in the KGH conference is obviously quite important. And I think this is where we have to keep in mind that we operate on in a real world and not on an academic background, because you can choose any sort of system you like, from biomass to solar, the combination or whatsoever, but it has to be compatible, for example, with a heat distribution system. It has to be obviously efficient. It has to stick with national or regional regulations, and this is easier said than done. Try to implement solar thermal systems in a traditional settlement in Greece and you will be crucified for this, for example. And it has to make also sense in terms of economics. In other words, we have to be able to apply an integrated design strategy for the building. If you have a heavyweight building envelope with high thermal inertia, very well protected, then you have to use certainly a heating distribution system that will be able to cope with this thermal mass, which means that you need either radiative heating systems working with big surfaces at low temperatures or the other way around. So you wouldn't be able to utilize some air-to-air heat pumps or something like that. And if you want to utilize the aforementioned heat pumps, which have excellent coefficient of performance nowadays, then you need to have a specifically designed heat distribution systems, and this is something which in the refurbishment of older buildings may not be always cost effective, to put it mildly. I come from the solar branch 25 years ago, so I always have a soft spot for solar thermal systems, but apart from the climate and the surface, this calls for reasonable economics. And if you need a solar thermal system like a combi system for heating plus something else for cooling, because we need both things in the Mediterranean, then the economics start to look complicated, to put it mildly. So it is a mixed integer problem that has to be optimized, and this is not always easy, but it can be done. Then we have also, of course, the newer trends. So far, for decades, we have been examining buildings as such, okay, perhaps a bit with a district heating or cooling, but more and more we move over towards microgrids, and we have integration of the building in the settlement. So you have to consider not only the building applied, or building integrated systems, but also the nearby system. What does your neighbor do? And you have also storage in the building. And if lithium-ion batteries get a bit cheaper, I guess I will have to quit my job as a thermal guy and start working a bit more with electrical storage, the way things go. So we have to consider things in a more integrated way, and this is certainly something which makes life interesting. And of course we have also to consider the architectural and aesthetic part, because not necessarily every building is interesting when it's packed with PVs and thermal solar and everything else. Still, and this is something which I think one cannot repeat enough, whatever system we may choose, whatever regulatory framework we may have, the strategy for having an energy efficient building has 3 steps, and they are consecutive ones. We need to conserve energy, i.e. reduce loads, have a well-designed building, thermally protected, airtight, ventilated, whatever. Then it comes to energy efficiency, reduce the demand, optimizing heating ventilation systems, control strategies, automation and controls, CHP, storage, whatever, and only then does it make sense to go for renewables. Because renewables, although they have become cheaper and more cost effective and more efficient, they are still an intermittent, sparse, not dispatchable energy source, so they have to be treated with care. If we approach the problem the other way around, from the right to the left, we may end up with a building that is an excellent renewable platform, but not necessarily an energy efficient building, and those are 2 different pair of shoes. The N word, So, how nearly zero should a nearly zero energy building be? Depending on the country, you can see some interesting differences. In Austria, a residence is not allowed to consume more than 160 kilowatt hours per square meter a year, and this value includes cooling, heating, hot water, lighting. In Germany, for example, it's not allowed to exceed 40% of the reference building, despite the directive's requirements. The Germans didn't put an absolute value. This does not include lighting, however. And if you go, for example, to Malta, you have 40 kilowatt hours only with heating, cooling, and hot water. So there's quite a big variety of values for buildings, for consumptions that allow a building to be a nearly zero energy one. And the question is, how tight should the regulation be? And I'm showing you now 2 slides. We are just about to determine our own nearly value in Greece, and we did the calculations for the ministry. So if you stick to, let's say, moderate U-value requirements, not really challenging one, let's say anything between 0.2 and 0.4 and 0.5 watts per square meter in Kelvin, then you end up with energy requirements of about 50 to 60 kilowatt hours per square meter in a year for Greek, typical Greek conditions. If you put the requirements higher, let's say a U-value no more than 0.3, for example, for the walls, then you have reduced energy requirements by, let's say, 50 or 60%. So in theory and practice also, it's worth going for a tighter U-value requirement before one starts examining the heating, cooling, hot water system production. And then we have 8 various systems, from conventional gas boilers to heat pumps, and from combined solar systems to whatever. And you see the yellow line which shows the renewable share, because the directive calls for a minimum something of renewables. And we can have anything between 20 and 50% without major difficulties. If you want to have 80%, you would have to go to biomass, for example. But this, of course, then is another question with respect, for example, to local emissions. Because if you do the ranking, and with this I'm beginning to conclude, Mr. Chairman, obviously you can have one scenario, let's say a well-insulated building with an air-to-water heat pump or a water-to-water ground source heat pump, and this would have the lowest energy consumption. The biomass would probably have the highest renewable share. The lowest life cycle costing would be for a very conventional, boring, high-efficiency condensing gas-fired boiler. It sounds trivial, but it's still very efficient. But still, if you have a different projection for the coming 20 years, because it's a 30 years life cycle analysis for the oil, or for the energy prices, or if you have, as I said before, pass-fail criteria in an urban area, using biomass is not always the wisest thing to do, then you have a different ranking. We speak about energy efficiency, we speak about requirements in order to meet the goal set, but as, for example, I'm sure that Dr. Bajic is quite aware of, energy efficiency is not a goal by itself. For example, we have to keep the well-being, thermal comfort, acoustics, and so on and so forth in mind. We don't build buildings to be energy efficient. We build them so that we feel comfortable in them. That's something not to be forgotten. We have to keep function and aesthetics in mind. We don't build buildings in the brutalist architecture way we did this in the 50s or 60s, I guess. And of course, we have to be able to validate things in terms of cost effectiveness. Otherwise, the rather competitive market will punish us. We also have to deal a bit with the energy poverty phenomenon. The latest figures by Eurostat show that about 70% of the European households do not have enough heating, cooling, and cooling for their residences. After 8 years of recession in Greece, we have 30% of that value. So we have to find cost-effective solutions, because if we don't do this, then we will have other sort of problem. The picture on the right is a very infamous picture. 3 years ago in the winter of 2015, after the tax on oil almost doubled in Greece, people started burning about anything they could. And if you start burning old pieces of furniture, you can see with what sort of smog you would would come up in Athens, VOCs and the particles that Professor Novak mentioned. So we have clearly defined cost-effective solutions, and not only on the life cycle term, because the life cycle costing is a very nice analysis for decision makers, but if you ask the guy who's picking up the energy bill at the end of the month, then he tells a different story. In that sense, I think that we have to look for solutions to have deep renovation schemes that are efficient, cost-effective, and affordable. And this calls a lot also for financing schemes and regulatory schemes, because any deep refurbishment, any deep renovation is a cost-intensive, front-loaded investment. And you can't expect someone to pay in advance 30,000 euro for a flat that he will, of course, amortize after 20 years, but who cares after 20 years? Finally, what I really would like you to take away from this presentation is that we are all good engineers, active scientists, successful industrialists, but it calls for more in order to move really in the new era of the zero energy buildings. After the political decision has been made some years ago, you need to have codes and standards. You need to have information and certification, for example, for engineers. You need to have incentives and financing scheme. The public sector has to lead by example, otherwise no one will believe anything that we are telling. Unless you get owners, users, and managers of facilities engaged, it doesn't really help. You also have obviously to get the financial service providers, i.e. the banks, engaged. Utilities are a major part of it, and I think it's quite interesting to see how the new perception of the role of utilities is in Europe. I mean, E.ON and RWE, they sold off their old coal plants and moved more and more into the energy provision services. And if we do all this, hopefully, with a bit of luck, this winding road will lead us to the zero energy buildings. It is a winding road, the road towards energy efficiency, but hopefully at the end of the day, it will lead us over the pass. Thank you very much for your attention.